So without further ado, I would like to introduce our panel. And they will each present for about 10 minutes, and then I'll have some questions for them, and then we'll open it up to the audience, questions from you. So Dr. Gunnar Carlsson comes to us with a dual affiliation at both Stanford and industry. At Stanford, he was chair of the Department of Mathematics from 1995 to 1998. His expertise is in topology, the study of shape, which he will tell us more about in a few minutes. Dr. Carlsson pioneered the applied use of topology to solve complex real-world problems. He's worked with the National Science Foundation as well as DARPA, and in 2008, he co-founded Ayasdi, which is an advanced analytics company working at the intersection of AI and big data for enterprise. Next to him is Dr. Henriette Cramer, who is a research team lead at Spotify. Dr. Cramer's PhD is from the University of Amsterdam in how people respond to autonomous systems. She's led research on voice interactions, bots, and recommendation contexts at Yahoo, as well as at the Swedish Institute for Computer Science. At Spotify, she works on the human side of machine learning. This includes topics such as the mismatch between humans and machines' models of the world, the feedback loop between data and design, algorithmic bias, and other ways that human decisions affect machine learning outcomes. Ranjay Krisha is a PhD candidate in computer science at Stanford. He's a researcher at Stanford's Artificial Intelligence Laboratory, which is called SAIL. His work brings together human-computer interaction, artificial intelligence, machine learning, and computer vision. At SAIL, he leads the Visual Genome Project, which connects structured image concepts to language. Recently, Ranjay and his team won a MAGIC grant from the Brown Institute of Media Innovation. He'll tell us more about the project, but in general, it involves an AI agent using conversation to learn more about the world. And our invisible panelist is Ryan Welsh. He is the founder and CEO of Kyndi, which was recently named one of the 100 most innovative AI startups in the world. Ryan's background is in applied mathematics, economics, and business, including an MBA from the University of Notre Dame. Kyndi is building the first explainable AI platform with a focus on serving organizations in government, financial services, and healthcare. Their focus is on serving agencies that require transparency and the ability to explain the reasoning behind their decisions. So without further ado, I ask Dr. Carlsson to come up.
Okay, thanks very much for the invitation to speak. So what I want to talk about today, and it relates to this human interaction aspect here, is that it's a different way of modeling data. And it's motivated by the needs of artificial intelligence as we've run into them, working at the company that I work with, Ayasdi. But just to sort of get the sense of what do we mean by artificial intelligence, I think for someone of my generation, when we first heard about artificial intelligence, what it concerned was taking problems which humans have already solved, for which there's a human template for the solution, and making it automatic, building it. In other words, where humans can solve it, and then we're just going to mimic that. And so it deals with things like what you see on the slide there. But where it's heading and where the important directions are now, in my view, is toward a much broader definition of AI. It's toward understanding where you have problems that people really haven't solved until now. We want to solve those. Those are bigger problems and more complex ones. So that, for example, complex problems include fraud detection and classification, cybersecurity. Genomics is one also where one is keeping track of extremely complicated data about large sets of genes. People really don't deal with those well effectively. In dealing with crimes, for example, one of the large global banks that we've worked with had 7,000 people hired to investigate questions about anti-money laundering. That tells you that it's a very It's an important problem, but also people don't handle it well because we're not very efficient at it if we need 7,000 investigators. So question is, what are the requirements for systems that are going to do this kind of broader artificial intelligence that really deals with these more complex problems? Well, the first thing is this, that a lot of what people think about when they think about artificial intelligence, there's a fear of it, there's a feeling, and probably with some justification, that they are black boxes. Many of the methods are, either understandable only by people with PhDs in very technical subjects, or in fact not understandable at all by anyone. And we may be able to show that, gee, they're performing something good in terms of prediction or classification, but we don't know they're going to do so going forward if we don't understand what's going on and in fact understand in a human way the outputs. Okay. So they're not acceptable for many purposes. For example, financial regulation. And this was actually where I first became aware of this problem, was when we started to deal with a bank that was undergoing the stress testing process. And they had built some very large and complex models. And it just turned out that the regulator said, you may believe this is predictive, maybe it is, but in fact, I don't understand it. And so I'm not going to sign off on this kind of prediction. Healthcare is another situation. We've all talked to MDs. My parents were both MDs. None of them that I meet are really very inclined to trust the black box solution that tells them when to operate or when to do what they're going to do. And perhaps with good reason, in fact. So. And then, let's see here, and social networks, yeah. So again, social networks, there's a lot of transparency that is needed in social networks. One wants to understand how decisions are made about what gets put up, what gets taken down, all those kind of questions. All of them require more transparency, less black boxness to them. And so in order to think about what does a platform, what is software, what mechanisms do you have to put in place to realize this kind of situation, in other words, to make software that is transparent, that does produce explainable outputs, and so forth. So, we've come up in thinking about it, and this is when I say we, this is at the company, we have been thinking about, so what characterizes, what are the different abilities that are necessary. One is the ability to discover from data without hypothesis. You don't want to have to come in and sort of have in mind already what it is that depends on what and try to fit a model to that. You want to try to find an unsupervised way of trying to understand the data. And this is where our contribution from Stanford comes, and I'll talk to you briefly about that. The idea of new ways of modeling data that are not algebraic in the sense that many machine learning algorithms are, where you're fitting equations and solving things with algebraic methods, but rather a different kind of modeling, which we'll talk about. Now, of course, you need to do that kind of discovery. You need to then be able to predict based on your understanding of the data, to predict and classify. Importantly, you need to justify your answers. You need to also understand what's going on inside your machine so that when it goes wrong, you can fix it, because all automatic things, in my view, go wrong at a certain point. Finally, you need to be able to act, and you need to be able to learn as the data changes and also as your users interact with the software. So what is an organizing principle for complex data then? Well, how can we talk? I'm going to talk to you now about that leftmost bit, the discovery aspect of it. And for us, it is that data has shape, and the shape matters. The shape is the first thing you want to know about your data. It tells you the organization of it. Sometimes it's the only thing you need to know. Sometimes it's the insight is actually in the organization. Other times you need to get kind of more quantitative and so on. So, and just to give you a sense of it, I think everybody in the room actually knows these ideas, but that the data has shape and the shape matters, because everybody has looked at this kind of situation where you have data that looks like this. This kind of data fits naturally along a line, and so there's a nice approximation here by a shape out of a line. And when you can do that, it's fundamentally useful because it allows you to predict immediately. It allows you to understand what variables vary with what and in what way. It's a really powerful mechanism when it's available to you. Unfortunately, the data doesn't always agree to lie on lines. Okay? Sometimes it will look like this instead. And when it looks like that, it doesn't fit along lines, but it's clear there's some structure there. It's broken up into 3 distinct groups. Now, that means, you may say, well, so there's no shape there. Well, yes, there is, because, in fact, this 3 discrete points, you might not think of it as a shape, but it is the best approximation in that case, different shape. Again, we might think we're done here. We might hope that we're done, but then we run into data that looks like this. This often happens when you have periodic or recurrent behavior going on in your data. There's shape here. It doesn't break into pieces. It's not a straight line. Instead, it is actually loopy behavior. And so you might say, well, great. Now we've got a third thing. Maybe we mathematicians or computer scientists or engineers can go to work and build loop detectors, just like we built clusters or linear regressors. But we'd have a gnawing feeling in the pit of our stomach that maybe we're not going to be done after we do loops. And then we come across data like this, and we're convinced that we really are never going to be at a final point in this, because here we have data. This might come up, for example, when if you have data from an airplane that's flying across the ocean. There's a normal mode, which is flying at altitude in non-turbulent conditions, and then 3 extremal modes, which might be takeoff, landing, and flying in turbulent conditions. So you need to build something that can cover all the shapes all at once. And so for us, sort of a toy version of that is an old problem that started the subject of topology, the study of shape, by a Swiss mathematician. He was actually annoyed at being asked to solve the problem, but nevertheless he did. The problem was, why would anyone want to ask it? It was, can you cross all the 7 bridges across the river Pregel in Königsberg without crossing any bridge twice? And the point was there's a lot of extraneous data in the problem here, namely how deep is the river, how wide is the river, how long are the bridges, and so forth. But he realized that you can build a simplified model on the left there, a network model, that makes the problem quite easy to solve. And so he was able to reason and solve it. We want to do the same thing for data. We want to recognize that there's a lot of extraneous data, and we want to build some simpler models, but they should not be models along what we usually think of as mathematical models, which are algebraic equations. Instead, they would be these kind of networks that Euler dealt with. And so let me just show you a couple of examples of that. We have collaborators at Mount Sinai School of Medicine who work on type 2 diabetes. And here you can see a network model for 11,000 type 2 diabetic patients. The finding from this is that type 2 diabetes is not a single disease. It is 3 diseases at least. You may have read over time, as you read the newspapers or Scientific American, articles that say things like, diabetes is correlated with cancer. Diabetes is correlated with neurological symptoms and so forth. Not so useful, that information, unless you can act on it in some way. And what these folks have done is that actually there are 3 groups of diabetics. One of them is heavily correlated with cancer. Another is heavily correlated with neurological symptoms and so on. And now it starts to make sense. You can now formulate treatments that are not required to treat all type 2 diabetics, but only those, say, that are correlated with cancer. Heads to precision medicine, which is one of the great things that medicine is moving towards. Here is another one. This is a modeling that comes from a group at Stanford, David Schneider's group, studying the progression of infectious disease. So he's been a great collaborator of ours. Question for him is, it's a different aspect of precision medicine. So imagine that you are being infected with malaria. You start out here, you're in your healthy state. And now you get infected, and you start to move. You're taking measurements of your physiology and genomics and so on. You start to move in a trajectory in that big space as you're getting sicker and sicker and sicker. At a certain point, though, the immune system kicks in, and now I start to return to the healthy state. But I don't return along that same trajectory. When I'm heading back to the healthy state, my immune system is kicking in. Everything is working hard. It's quite different from the trajectory that I had when I was getting sick. And so it is this loopy kind of model here again. And the important part here is that you might ask, can't we just encode this by time? Can't we say this happens at day 1 of infection, this happens at day 2, and so on? Well, actually, it's not so uniform as that. Those things don't move at uniform speeds. The disease doesn't progress at uniform speeds. But maybe more importantly, we don't actually have the information about when you were infected. So we need to have an invariant way of saying, where are you in the process as opposed to where are you in the time? And that's what this model has allowed him to do, and to understand the kind of function that is going on at a point. So, and then finally, let me just end with, this is kind of something that is currently very exciting to me, which is trying to understand what's going on inside and outside deep learning. So deep learning is a fantastic technology that's been, one reads a lot about now. It has had tremendous successes in classifying images as, digits from 0 to 9, or dogs versus cats versus giraffes, things like that. Very, very powerful mechanism. But it is a black box. It restricts the utility, and it also has some problems with it. Some problems are kind of instability, that if you change an image a little bit in a way that we wouldn't perceive as being different, nevertheless it can foul up the classifier. So it's called adversarial attacks. And so you can't really diagnose what's going wrong because you don't understand what's going on inside. And so just to finish then, the methodology that I'm talking about, one of the things that I'm very much engaged in working on is precisely gaining that understanding by trying to understand the shape of the set of states that are going on inside the machine, and also the shape of the outputs, and hopefully generating better features as inputs that won't be subject to these adversarial attacks. So to my mind, though, back to the theme here, the idea that you can model data by something that is more human interactable. So rather than equations, that it can be networks that you can interact with on the screen in the way that you would with Photoshop or Illustrator, in a way that allows you to get explanations for groups very quickly and allows you to get just a better understanding and therefore better justification and so forth. So let me stop there.
Hi, I'm Henriette. I'm a lab lead at Spotify. My team mostly works on voice interactions, and personally also focusing a lot right now on algorithmic bias and how to translate between research literature and industry practice. So my original background is actually in how people perceive autonomous and adaptive systems, and actually also the impact of transparency features as well as social behaviors on those perceptions. Over time, worked in different academic and industry contexts with robots, location-based services, and especially search, recommendations, and conversational interactions. And in all of those contexts, something that's really, really interesting to me, funnily enough, also is a loop. A feedback loop between the systems and the users that actually interact with them. So anything that learns is adapting. That means that the behavior is changing based on the perceptions that you have on outcomes. You change your behavior and the system learns and changes, and you have this never-ending loop going on. So for me, what's very interesting there is what are the data and design decisions that you can make there to actually influence that loop? And what in these perceptions in that loop lead to us, a system and a users together figuring out we want to work together? So you want perceptions of competence, you want perceptions of our intent, our goals are the same, and you want the perception of, I'm not going to socially embarrass you when I take you somewhere. So in a music context, music is really emotional. It's personal, it's deeply human. You may remember the club you went to, or your favorite song, or your first dance at your wedding. That's obviously not what a system would know about this music, right? It may know characteristics of the tracks. It may know that different types of clusters of people listen to these tracks, but it doesn't necessarily capture all of these memories. So in some ways, we need to teach the machines there. And there you already have this gap of what can we teach and where do we actually need some more human expertise. And something that, for example, for me is really important to emphasize is that understanding the culture of different types of music is extremely important, and we can't send a nice system to a club or to a concert, or like talking to different artists about what they actually care about, right? So that's why there's always a collaboration between, let's say, our machine learning efforts and the editorial teams and the data curation teams that actually understand the culture, understand the data, and understand the machine learning efforts. So different roles there need to come together. So the first part of perceptions of competence. Obviously, a machine learning system needs to learn. Learning involves mistakes. So errors are unavoidable there because otherwise you can't improve. And like Gunnar just mentioned is okay, normally you teach a machine, right? Is this a dog or is this a cat? But then in a lot of contexts, there is no ground truth, right? So in music, if I go, give me something really awesome, and it needs to be the live track. Do I mean this awesome festival I went to? Do I mean this wonderful symphony? Or do I mean this nitty-gritty punk bar? All of these are correct answers, but I need to learn when this actually applies. Obviously, then there's the when should I actually know these different parts? So in the past, I worked a lot with location-based data and looked at the characteristics of different types of locations. And let's say you have this photo. If I would have some fantastic image classifier, it's like outdoor, it's a beach, but actually for me, it's California highway. That we could actually figure out, but not for the image, right? But it's a road trip, and that's my wonderful partner. You wouldn't know that either, right? So when we actually look at the different characteristics of these data sets, you find that the usage cultures will really influence the characteristics of that data. So again, you need that human input of what are the characteristics of these data sets that we are trying to use. And definitely also what's missing. So like you just mentioned, Karina, that, hey, when we were talking before, it's like, hey, what isn't surfaced is just as important what you are actually recommending or seeing as a result. So based on, for example, your training sets, your different APIs that you may be using, the different components that you bring together, different things become more or less accessible. So we had a wonderful intern last summer, Aaron Springer, who actually looked at, hey, what if you start using all the standard components for example, voice interactions? What type of music become really hard to ask for? Some of the most impressive examples were, for example, Pentagramophone Walhalla, which when you use a standard ASR service, you get something like Play Pentagram of Fame by Walhalla now. This may be an extreme example, but when we actually looked at most of our popular tracks, it turns out that especially genres that have more creative linguistic practices, let's say country or hip hop, also become less accessible. It turns out you can actually detect this and do things about this. And something that was interesting to us is quicker, simpler methods may actually get just as impressive results as things that may be much more complicated from a modeling perspective. So also the goals and intents. Your machine learning system has to optimize for something. Defining a goal is absolutely not neutral, even with a thermostat. Who in the house wins? Is it me or my partner who gets to be either too hot or too cold? You have to make some sort of decision there. You are measuring something. But what are you measuring? And for which of these purposes will it actually work out? That definitely also means that you need human judgment there. So something that sometimes is a bit strange to me is people go, everything is automated, it's great. But no, you want to have human judgment there of people actually know your domain. You're not replacing them, they're helping. You may have seen Microsoft's Tay, the bot who learned. Does anyone want to tell what happened to Tay? Is anyone there? Go ahead. So if you would just, so Tay learned from what people said to it. From an engagement perspective, if you would just count the number of engagements, looked fantastic. If they had not had the human judgment of the quality of what Tay was actually saying, they would not have realized they needed to take it down, right? And something there is that basically all of these different decisions, or non-decisions in some cases, lead to certain types of characteristics, which means that any data set and any algorithmic outcome in some way is biased. It has characteristics. Whether good or bad, you need to figure out what these characteristics are. We have literature on this topic since at least '97, when we did a literature review of what types of frameworks would actually apply to our context. Lots of translation is actually necessary. So one of the big things here is, how do we bridge this gap of all of this super impressive literature into industry practice? And something that a group of wonderful colleagues have helped out on is actually, hey, can we just transform this into what are data characteristics, what are outcome characteristics, and in the middle, what are the characteristics of the team and the models that we are picking? What are the questions that we could be asking ourselves in different stages of the development process? And definitely, like, something, in case you are writing papers on this topic, something that would super help is actually, what is the summary of 3 bullet points you want teams in practice to take away from this? So now you know my perspective, and what we actually have been doing is trying to figure out, how can we have these simple ways of asking these questions? What are our goals? How do you gather feedback? How do you measure quality? Who provides your human perspectives? And how do you react to behaviors that you may not necessarily want to encourage? And looking forward to lots of conversations about how we actually bridge this gap.
Hi everyone, my name is Ranjay Krisha, and I'm a PhD student in the AI lab, and I teach a course on computer vision in the fall. Most of my research is work related to human-AI collaboration. How do you build systems where both humans and AIs can both coexist and help each other achieve tasks? So today, I'm going to try to connect my talk today with the talks that were given. So to start off with, something we're all very familiar with is that AI systems are sort of seeping into all aspects of our lives. Right? Remote interactions with a lot of companies are now being automated by call center bots. We have specific kinds of machines that can cook us certain meals in specific kitchens. And we also have therapeutic bots that can talk to us and help us combat depression. When deployed, all these AI systems have to interact with people. Unfortunately, when these systems are trained, they're trained to optimize for performance and not optimized to train to interact and understand the social interactions that people want. And this has led to a lot of failure cases. One of the most widely talked about failure cases, the one that was surfaced by ProRepublica, where they found that a computer program found people of color to be more likely to be future criminals than people who are not. So what they found was that the reason these sort of computer systems got away with being biased is because they were evaluated on biased data sets by using biased protocols. And when you actually take a look at all the data sets we have today, almost all of them are biased. Right? So this has led to racist classifications in images by Google. This has led to different kinds of policing strategies that are also inappropriate. This has led to gender biases where women tend to receive job ads that are less paying than the ones that are surfaced to men. So when you actually start looking at where these biases are coming from, it's really daunting. Right? So they can come from all over the place. There are a bunch of different sources where these biases can seep into our programs. For example, reporting bias and selection bias was a huge problem recently when we were analyzing a lot of these image generation machine learning algorithms that we were building, we found that a lot of these images that were generated were of faces of white people, and for some reason, they looked a lot like George W. Bush. And when they analyzed it, they found out that those data sets were actually collected from Yahoo News corpus when he was the president. What you get to see is that a lot of these training data that we collect and build data sets with, they tend to highly represent those people who are in power. And so how do you combat this issue? A lot of recent work has sort of taken a look at how do you tackle bias by introducing ways of creating more transparent systems. And these methods that have been surfaced recently to create more transparent systems have taken an approach that is both statistical as well as judicial. Recent papers from lawmakers have sort of analyzed ways that we can still treat AI systems as black boxes and still be able to leverage ways of surfacing the transparent biases that might exist. So to be more concrete, some new techniques have come around that have said that let's treat these AI systems as black boxes and let's prod their inputs. Let's change one small factor in their input and see if the output changes. For example, if you were looking at whether to give someone a loan or not, and the input you change by changing their race or their gender, and if the AI system changed its outputs, then you know you have a biased system if everything else is kept the same. So a lot of these systems have been really focusing on creating more transparent training procedures. But one thing that I've been really struggling with is wondering if transparency is necessarily enough to garner trust. Even if these systems were transparent and we knew what biases exist, can we trust these systems? And the reason I'm a little hesitant about that is because it seems like there are so many sources of bias that it's really difficult to solve. I don't know if we'll be solving this problem in the near future. So if we can't solve these problems of removing bias from our systems, maybe we need to take a look at other ways of creating trust. And when you look at how people build trust with one another, they trust other people or other systems that behave as they expect them to. So instead of understanding the problems that a system can have, maybe we should build our systems so that they can incorporate feedback from people that can take a look at the mistakes that were made and have the users who are working with these systems pick out those mistakes and tell you how to fix them. So systems that are dynamically learning and not just statically deployed. That's the kind of systems that I am interested in building. So enabling systems that can interact with and learn from people is a social problem, and it's also technically unsolved. And so what I've been really focused on with my team recently is building ways in which we can interact with people naturally and learn from them. And the most natural way to interact with people is through conversation. So we're building a conversational agent that can talk to people about things that it doesn't know and hope to learn from these people. So what it's trying to do is optimize two things. The first one are its AI needs. The AI needs are things like performance that people have been traditionally focused on. How do you understand and gather data that'll help you improve on a task? And we're trying to balance that with what people are willing to engage in. What are people willing to teach these AI systems? What are things they're willing to talk about so that we could learn from them? And so to deploy such a system, we've been taking a look at a basic computer vision system that's trying to understand the visual world. And we've deployed a system on Instagram. For those of you who are unfamiliar, Instagram is a photo sharing website that's very popular. And the reason Instagram is great for our project is because it's a place where people upload images that they're really familiar with. It's pictures that they've taken themselves, usually of themselves. And these are pictures that these machines are completely blind to, because these pictures aren't represented well in the data sets that we already have. So it gives us a nice sort of framework where we can talk to people, engaged with them in the wild about their pictures, about the contents that they care about, and learn what we don't already know. So let me sort of break down what this interaction looks like. Let's say someone uploads a picture, and usually when you upload pictures, you don't really talk about the contents of the image, you just talk about some sort of story around it. So here someone says, look who's excited today. And our AI system comes in and realizes it doesn't actually know what the breed of the dog is, but it does know that it's looking at dogs. So it says cute dogs, establishing some amount of social rapport. And then it says, are those Labradors? So it has a prediction in mind, but because it doesn't know if that prediction's correct, it goes out and asks people to help it correct its predictions. And based on these responses, we can figure out when we're incorrect and update our system dynamically over time. Of course, we can do this for new concepts as well. If we don't know what things are made out of, we might ask, what is this table made out of? And learn about concepts like mahogany that we didn't know in the past. So this is what the interaction looks like. Now let me talk about how do we actually learn from it. So when a question is posted, if it gets no response, that's a negative reward. That means that that's not a good question to ask. People aren't willing to engage with that question. And if they're confused by the question or feel like it's too unnatural, they might still not respond, and that's another example of a question that we shouldn't be asking. And over time, what we're hoping to show is that our system will learn to ask questions that are very natural, that look like they want to engage with the people who are posting these pictures, and learn from them by sort of making a natural connection with them. So this is what our training loop looks like. We are analyzing pictures coming in from Instagram, and whenever we find something that we don't know, for example, here we know that there's a picture of something on a tree. We don't know what animal is on the tree. So our system goes ahead and generates a bunch of questions that try to get that answer. And then it picks the question that it thinks is most likely to receive an answer. And not just any answer. Unlike Tay that was trying to just engage people, we're trying to actually get an answer back from the person that we can use to learn. So it posts that question that it thinks will give us the correct answer. And if the person doesn't respond, we get a negative reward. If the person responds with something that is not the answer, we again get a negative reward. But if the person does give us the correct answer and tells us this is a red panda that's on the tree, then we can use that information and add it back to our existing knowledge. And over time, what we're doing is building out these large deep learning systems that are balancing both its knowledge value, the needs of the AI, what knowledge it already knows and what knowledge it should go after, and we're balancing that with human interests, things that humans are willing to engage in so that these systems can learn organically by interacting with people in the wild, and in the process build trust. So we've been interacting with people for a while now, making about 100 posts a day. We get people to talk about the flowers that they post, about the food that they're eating, about the materials their kitchens are made out of, and even about what time of the day their photos were taken. And currently, we're getting a response rate of about 27%. This project is still very new, and we're still analyzing ways in which we can figure out exactly what type of questions people like to talk about. So in conclusion, I think building trust is a slow process. And we can't understand and have a good view of all the biases a priori. We need to actually interact with people in the wild, figure out which biases come up, and build trust slowly through a social process and not just a technical one. And this is a project with my two advisors, Michael Bernstein and Fei-Fei Li, and my team of researchers who make this all possible. Thank you.
So I'm Ryan Welsh. I'm the founder and CEO of Kyndi. Kyndi is coming up on a 4-year-old company. We were just listed as one of the 100 most innovative AI companies in the world by CB Insights. We're also considered an innovator by IDC in the cognitive AI platform space. So my background is actually in mathematics. I was a quant back in New York for 7-8 years. I helped save the universe, not blow it up. All right, relax, everyone. So I share that because when I went through that experience, it was actually the weekend that Lehman Brothers went down, and a partner came to me and he said, Ryan, could we get a handle on our clients' exposure to Lehman Brothers debt? And in 3 days, I had to read an amount of information that when I left for business school 3 years later, I was still reading. And really the only bank on the street that really had a proper handle on their exposure was Goldman. And the rest of us were just kind of doing keyword searches and all these different things. And I bring that up because I then went back to business school, and thank you for having me. I went to Notre Dame. And when I got out, I kind of had this macro thesis that it seems that we're the bottleneck in this modern production process because we can't read and understand information any faster than our parents or grandparents. And it was really interesting for me. I kind of looked at all the technologies that I had, and it just seemed like if we were to compare this modern knowledge process to this industrial process, where you kind of stack up these raw materials and you manufacture them and then you ultimately turn them into some finished product. Effectively, all these tools that we have are just stacking up the raw materials, that information in front of the manufacturing process, but we actually haven't gotten any better at reading it and understanding it and turning it into knowledge. And it was with that I started Kyndi, and really I wanted to accelerate the adoption of AI throughout the enterprise because I thought it could be transformational. But one of the fundamental things that I thought that was necessary was I needed it to be explainable. And for me, for artificial intelligence to thrive, it must be explainable. And I pause because probably the first thing that you're asking is why. Right? And then how. So I'll get to the how. Yeah, it's super, super interesting. And I bring that up, and I love doing that little shtick. Sometimes I'll go over and sit down for a little bit, and then get up, and it'll be super awkward. But the point being is that there's a lot of arguments out there, and I've seen them more and more. Particularly a partner at Andreessen Horowitz published on this in the New York Times. I believe even Peter Norvig over at Google has said this, that we as human beings really can't explain our decisions, so why should we make machines explain their decisions? And my argument kind of comes from the customer perspective, where customers want their decisions about them to be explained to them. And I've found that more and more with our customers. So I think that for artificial intelligence to thrive, it has to be explainable. And really, the reason why that is because we are meaning-making machines. For all of you that have taken Tony Robbins and Landmark and all these things, we consistently make meaning of things. And we go through our lives making meanings of things. And really, AI is meant to serve us. I think so. Amplify our productivity. I hope it can amplify our productivity to a point where I can stop working 80 hours a week. But who knows, right? But the point here is if it's meant to serve us, then it has to interact with us in a way that adheres to how we do things. And let me kind of give you, and I'll get into the how, but let me just give you a use case and kind of how we think about these things. So here's a use case. So we work with government, financial services, and pharmaceutical companies. So here's a use case where we were analyzing science and technology documents. And there's really the extraction pieces of the use case where you're extracting authors. There's well-known techniques for that. Then we have a ranking algorithm that's quite unique. But here's the thing that I'm most interested in is this automated scoring of technology readiness level. So when we automated this process for them, it was about 150 questions that ultimately went into answering whether or not a certain technology is between 1 and 9. Maybe the professors in the room know technology readiness level in the NASA scale. But when you make a decision, when you make a classification, when you ultimately reason about some document, here it's the triangles, what the analysts wanted to know was, why are you making this decision? Why are you ultimately doing that? So effectively what we do is we combine really two aspects of AI. Statistical machine learning and knowledge representation and reasoning, and we couple them together in a new way, right? And I can dive in on exactly how we do that. But effectively, we're able to machine learn what we call proto-ontologies from data. We machine learn these structures. We induce the structure from the data. We actually adhere to John Soa's conceptual graphs, if people are familiar with Soa's work. We then stick those graphs into a large graph engine that scales to tens of billions of nodes. And we're able to structure map in that graph remember, what was the paper back in like 93, 94 on structure mapping engine, where you're now in like x cubed time. We're able to now traverse this graph in sublinear time. So we have some new techniques that allow us to take the initial questions around technology readiness level, project them through the larger graph, and unpack the graphs that we find in there back to the natural language as we packed it into the graph. So that analysts are able to click into the system and ultimately determine, hey, thumbs up, thumbs down, was that question right or wrong? And for us, that's been really key. I think that trust is a product of consistency and time. And in the absence of time, as government and some other folks lack the time to ultimately get this trust, you need to be able to explain yourself. And here's some data that we pulled I think people would find fascinating. So how long does it take to trust a machine? So we were able to collect data, and this is from first working with the system and not having any knowledge of what this system could actually do. So what we saw was that analysts, when they first got the system, and this is indexed, so you couldn't actually give away the real numbers, but ultimately what we're judging here is how often do people click into those triangles to determine are these right? And we saw for the first 3 months, or actually for the first month, it was a lot. They really didn't trust the system. And then you saw diminishing spot checking over time, and it actually kind of asymptotes down here, and you'll see that they need to click into the documents, ultimately do their work. But it was fascinating for me to see that from never really using advanced AI for an application that is critical to certain mission needs within the government, that just after 3 months, people are willing to now trust a system, which is I thought was pretty quick. Some people may think that's quite long.
You're saying none of them blew up?
Which blew up like which way?
Not
Good.
trust,
No, so they have the work to do anyway, right?
that's
So.
not as a trust, that's just being forced.
No, totally. So if you have the work to do, you either have two options. You can either trust the system, and maybe I'll give you my churn rate numbers to determine people churning off the system. But the people that stayed on the system, and we actually have a negative churn rate, started to trust the system after 3 months, and it was just diminishing clicking into those documents. But what's key, and when I bring up explainability, because I always get caught, and everyone says, all right, so you think fundamentally it needs to be explainable and everything needs to be explainable all the time. And my thing is, no, there's varying degrees of explainability that you need, right? Like if Google gets the classification of my cat picture, and I have a really cute cat, by the way, incorrectly, I'm not really worried about it, right? But if the system decides to do a drone strike, make a decision, well, maybe it should be explainable, right? Or autonomous vehicles, legal sentencing, medical judgments, loan decisions, right? I think there's varying levels of explainability, and there's varying use cases for which you require explainability. And we always seem to be, at least for our business, obviously to the right of this, because it has a high impact on people's lives. I'm sure people are very familiar with this slide. This actually comes from DARPA. And the reason why I shared my background in the beginning is because I don't come from artificial intelligence. I haven't studied it. I didn't even study computer science. I was just a math guy. And I paired up with a few pioneers in the field, including John Soa, who's a researcher with us, and Benjamin Grossoff, who some of you may know, and people like Aaron Majumdar, who was a part of McCarthy's Formal Reasoning Group here. And really, I share that because I kind of looked at it from a problem perspective. How do you piece these things together to ultimately achieve your explainability? And I feel like one of the biggest challenges that we have as an AI community is we have all these technologies, and it covers a bunch of different aspects of intelligence. But one of our biggest problems is that we hate each other. Like, why is that, right? And it's fascinating, even today, that when we come out, and I'm talking about fusing these two paradigms of AI, and there's multiple paradigms, but kind of fusing the two main paradigms together, people just completely reject that as a possibility. And it's really fascinating to think about. Even in my engineering team, I'll get fights among the machine learning guys and knowledge representation and reasoning guys. So I think to achieve explainable AI, and I really appreciate all the talks earlier, and in looking into that black box, and I'm fascinated by a number of companies that are using deep learning to understand the deep learning network, and I think there's interesting areas there. But really, I think there needs to be 3 legs to the stool. There needs to be machine learning, there needs to be knowledge representation and reasoning, and maybe that NLP as the glue holding everything together. And I'm hopeful, and I guess if I had a message to maybe students in the room, is that don't just focus on one type of technology. Get a broader understanding of all the tools in your toolbox so that when you use those tools for specific problems, you know which ones are good for that problem. And I find it fascinating now, and we're seeing this more and more, that the statistical machine learning folks are talking about knowledge. And you start to see people from DeepMind talk about knowledge representations in transfer learning, and you're seeing a lot of people start talking about the knowledge representations. I feel as if we've swung in one direction, and we're kind of swinging back in the other direction. And again, I would just encourage everyone to look at different types of artificial intelligence and how they apply to different problems. And again, I fundamentally believe that for AI to thrive, it absolutely must be explainable, specifically for use cases with a high impact to the individual. So thank you very much.
I think what I'd like to do is start with the human-AI collaboration, which is sort of the key sort of theme of this panel. And from my understanding, the idea is that we're better together. So it's kind of each, the total is greater than the sum of its parts. But in each of your research and your work, how do you think about the role of the human and the role of the machine? Do they have separate roles? Do they kind of interact? And we could just kind of go in.
Sure. So for humans in the use case of the one that I showed, they were analyzing these science and technology documents and assigning scores to them. And these are PhDs that speak several foreign languages. And the last thing they wanted to do was just sit there and take 2 hours per document and do 1,000 documents, 2,080 working hours in a year, 1 year scoring 1,000 documents. So if I can do them in 7 hours, which we do, well, then now they get to spend 80% of their time being creative and resourceful versus spending 80% of their time doing mundane work, preparing the information for analysis. So I do think it's a better together situation, and we kind of elevate the work that we do up to the more creative and resourceful work, which I think is unique to human beings.
Okay, so in terms of these collaborations, from what I've seen, a lot of these systems can be broken down into 2 camps. The first camp involves AI systems that are built to specifically help humans improve on a particular task. And your example sort of fits into that category. And then there's the other camp, which is using humans to improve AI systems. So that's where I guess my project sort of fits in. I still feel like there's a missing component to how collaboration should be done. I think real collaboration between humans and AI systems should include something along the lines of what you're talking about, which are these loops where you have these AI systems which are improving over time, are being taught by humans to improve over time. But as they improve, they make people more and more productive. That can help them more and more. So it's not one helping the other, it's them sort of working together and improving each other. That's the kind of collaborations I would like to see.
So, like I already talked about, something that is extremely important is what are the different roles, the human roles that we need to actually make this collaboration work, right? So obviously you want to support the people who actually know the different cultures, the different subcultures who deeply, deeply care about different types of music. That's one part to it. There's also different human roles that you need in your organization. So who are the people that can provide you the very, let's say, training data that doesn't necessarily come from experts? Who are the people who can make the translation between that training data and what your machine learning teams need? And what are the people who actually form that bridge on the editorial side between the music cultures and their editorial view of the types of music they would love people to actually discover. And it's basically a layer cake of all these different roles that work together to actually support making sure that different artists get more exposure and that there is an editorial point of view.
So, but just before we go on, how do you decide how to break down those layers? Yeah.
So that really depends on some of the open questions that you may have. It's, let's say, in a context where you want to know how someone would ask for music. You don't necessarily want just okay, give me some grindcore from the 90s is probably not necessarily what different populations will ask for, right? So it's that combination of, can we understand the expert view of the world, but also how different people in different markets would ask for the type of music. On a personal note, something that, for example, was very frustrating moving from Western Europe to the US is all of a sudden genres have different names. I didn't know to which concerts to go anymore. I didn't know how to trust a flyer. So there's all this translation between different types of people going on there.
Yeah. So on a fundamental level, I think probably we would all agree that the role of artificial intelligence is to, in some way, improve human well-being. That's the ultimate goal. And you brought up the fact that, well, there always has to be an optimization problem. And so somehow we want to optimize human well-being. But the trouble is that human well-being is a very hard to understand target. It varies from person to person. It varies from time to time. And it may also be affected by whatever artificial intelligence we're putting into place. And so I would want to make an argument in favor of, let's kind of broaden what we do beyond just optimization. Let's also think about systems that allow you just to avoid the really bad stuff. In other words, maybe we don't have to optimize all the time. Maybe because it's too hard, because we're going to be, we're going to want to put our favorite model in place and optimize that, and we think it's a proxy for human well-being. But maybe it isn't, and there are lots of corner cases where it's not. So I would want to argue for methods of analysis, kind of unsupervised methods with explanation for what the phenomena are, but that capture just avoid the bad stuff, and that means that you have to go beyond capturing. Optimization typically captures what one would think of as the strong signal in the data set. You really also have to understand some of the weak signals, because the weak signals can create small pockets that are really the bad stuff that you want to avoid. So, yeah.
Yeah, I think that, we've been talking about transparency as a way of creating trust, and we've been talking about it as a way to diagnose what's going wrong. That's kind of from your perspective. We've been talking about it as a way to kind of unpack what's going on in the black box. How do you kind of create the trail? And I think actually let's go backwards this way. So in your organization, how do you create the transparency, and what are some of the other elements that are important for creating trust? And also, kind of at the second level, who are the constituents that you're trying to sort of create the trust?
I'll just give a couple of instances of that. Yeah. So, and I think I mentioned in my talk that sort of a very enlightening moment for me was to deal with a bank that was undergoing the stress testing process. And there, as the regulators did not trust the complicated machine learning model that had been put out, and it was optimizing something, and probably not doing too badly. But they were willing to sacrifice some of the accuracy. And in fact, because they didn't actually believe that any model would be that accurate anyway. But the idea that you would sacrifice a little bit of accuracy for having a model that, instead of involving 1,000 variables, that involved 3 variables, and each of those 3 variables was named as being representative of U.S. stock market indices or credit spreads or whatever, that you have 2 or 3 or 4 variables, much like a physics situation where you've got a few small variables and they interact in a particular way. And they said, look, we know it's not going to be exactly as accurate on your training data as your model, but we believe it. We believe we can understand it. And so, that's one form that it takes, which is where the answer is explainable. there's another aspect to which I think is also this diagnosis aspect. If we don't, all machines go wrong, and you don't just want to have information that, yeah, it broke. You want to have information about why it broke and how do you fix it. And so if you don't understand it, you can't do that. And my feeling is that becomes in itself a data analysis problem. Studying the states within the machine is its own freestanding data analysis problem, which is really actually very, very interesting.
I'm going to riff off of that. Something that has been really, really interesting to watch, especially in the FAT-ML research community, so focused on fairness, accountability, and transparency in machine learning. A lot of work there that was, for example, presented at the FedStar conference was focused on, hey, how do we break down accuracy into, let's say, accuracy or performance in different types of situations, and how do we figure out where aren't we so great? And in an industry practice, there's always the question of, okay, can we measure that? And how do we then prioritize which problems to solve first? And yes, that in itself is a huge problem that could use much more support. Like, what am I measuring? For whom am I measuring this? And how do I then decide what to fix first?
So I think I wanted to go back to one of the points from one of my slides about transparency. There has been work where we've all talked about how AI systems are a black box. I still think that even if they're not explainable, there are ways to interact with AI systems that might help us uncover problems that might exist. So specifically, if you can break down the inputs that go into these systems into multiple factors and be able to control those factors, you can observe the output and figure out what went wrong. So you can answer questions like, what are the main factors that go into making a particular decision? And why two very seemingly similar inputs receive different outputs. If you can break them down into these individual factors, then you can figure out what factors cause these flips. And if these factors are a result of particular problems or biases that exist, then you know that that's something you need to fix. And building benchmarks like that is, I think, the way forward for a lot of these transparency-based problems. It's nice to have such a formulation because you don't necessarily need to know how these systems are built. You can use any sort of system out there, treat it like a black box, and just prod it to figure out exactly what are its problems.
Yeah, for us, it's working with language in its complex space, right? So you kind of take these qualitative measures and you put them into some quantitative numbers so you can do cool stuff with it, right? The challenge is staying at that level of abstraction and not blowing out in your computational resources, right? So when we talk about structuring language, we literally take all of your data and we turn one-to-one match all of your sentences into some massive term structure. And then we just do projections through that graph. And then when we return subgraphs, we unpack those graphs into the original language. And you can add a because in front of it. And now you have your explanation, right? So an example is for TRL scoring, to get a TRL 5, I believe was the technology demonstrated in a laboratory setting, right? So the document may not actually say laboratory, may not actually say technology, but if it's like written by two professors at Stanford, even if it was done in the cafeteria, it was a laboratory-like setting, right? So you can now find the pieces of the document that answer it in a way, and then you just highlight that for the analyst to look at and say, yes, that is right. These are two credible professors from Stanford that were doing the analysis in a laboratory-like setting, and they were reporting back on this analysis. Thus, it was demonstrating a laboratory-like setting, and it's a TRL 5. So it's really just working with language at the most complex level and not having to reduce it down and lose a lot of information.
So I'm hearing, a lot about the different ways that, the concept is bigger than transparency, right? There's reliability, there's consistency, there's justification, there's accountability, and so this kind of that trust is being generated by taking this concept and kind of unpacking it more and more and sort of creating these systematic models where we understand what's happening with the artificial intelligence, what's happening with the machine learning, how the process is working. And then at the same time, I'm hearing that that humans are complicated, and that, that there's all these levels that are subjective, and and they vary, and that our opinions are subjective, and that we're kind of still figuring out how to negotiate those two things, and that it's sort of a dynamic and iterative process, and that there's a feedback loop and so forth. And sort of before I open it to audience questions, do you have anything to kind of add to that picture and kind of go?
Yeah, I can. That's
go back this way.
Well, that's absolutely right. So like with our thumbs up, thumbs down UI, there's certain analysts who would disagree with another analyst who's the same level of experience and training. And it's how do you have this kind of, people are complicated, and how do you have this kind of personal explanations for folks? Because both of them could actually be right.
Yeah, I think I agree. I don't think there's one solution to this problem. For every single individual person, you would need to come up with different set of ways of building trust. And it's complicated. And I think treating this as one simple, gigantic problem isn't the right approach. You should be working on having multiple solutions for different groups of people, involve many different groups of people in these problems, and that's the way forward.
One extra complication here is that even the design of the explanation features and the feedback features in themselves, so is it thumbs or is it stars? Yeah. Even that very subtle difference will result in very different training data. So having had that background and seeing how people in my earlier research reacted to, what if you add a Y? And they read an explanation, and all of a sudden their training data looks very different. Oh no, what have we done? Right? So really that understanding of how do you design this, does it actually impact what we get back, and not just, well, we explained it, let's see what happens.
So I think it's really important to keep in mind what the goal is at the end. Again, it's to increase human well-being. I think a lot of times you read marketing about artificial intelligence where it sounds like the goal is to just simply create an artificial human. And I don't think that's the goal. I think we want to keep in mind that the technology remains in the service of people. And I think if you do that, then you'll realize that you'll need ways of monitoring the technology to see that it's doing what we're doing, and also to recognize when there are feedback loops. Supposing that one part of human well-being is in fact doing some task by yourself, then you wouldn't want to replace that.